Okay, so let's start and welcome to the fourth summer school on machine learning and electron microscopy. So it's organized by Professor Gerdusher and myself with the participation of and very active participation by our teams. So they will introduce themselves when they have the presentations and kind of will give a little bit of the background of what brought them to this field and made them our partners of crime and organization. So first of all, thank you all for joining. So the response to the school announcement was very impressive. So Allah has made a map of where the participants are coming from, or at least people who want to be participants. We realized that for many of you, this would be late at night. So this school would be recorded. It will take us some time to clean up the presentation, but the recordings will generally be available. But for the time being, it's great to see the response along the globe. Before we start the school, kind of the official part of the school, let us... can please everyone mute themselves online? So let's briefly talk about why electron microscopy is special and what is the future of automated microscopy. So for about several thousand years, okay, let's sort this problem. Okay, let's do it this way. So for many thousand years, people have observed the universe, right? So they saw the stars, they made some connections between how the stars moving and what happens in the Earth. And this observation basically allowed to build the correlations, right? So if the moon is in a certain position, that Nile will flood, and that's the time to plant barley or whatever. But then this observation started to teach humans to think about how the universe is built. So we went from correlative observations to Ptolemean model of the universe to Copernican model, and then humans started to think about the numbers. So that was the Kepler laws. Then Newton built the mechanics. There is an argument whether we would discover the special relativity from the astronomical observation, but we did prove it from the astronomical observation. So basically, a big chunk of science has been made based on the observation of the universe. So in 20th century, the science has become slightly different. So science has become all about the big facilities, X-ray scattering, and the language of the condensed matter physics and the language of the scattering is the same language. So the X-ray scattering data and the way that we talk about the structure of crystalline solids, the way that we talk about the ozone structures, quasi-particles, is the same language. So now we're going to the 21st century. And we pose that the 21st century would be the century of microscopy, simply because it's not enough to study materials on average. We really want to understand them on the level of the individual atoms and chemical bonds and so on and so forth. And in fact, interestingly, this diagram shows the development of the aberration correction electron microscopy. So by the end of the 20th century, aberration correction just became a thing. So what you see on the top left is one of the first aberration correctors. If you at some point go to Professor Dusher's office, so he can bring it, you will actually see this corrector or very similar collector in life. And for the 25 years, electron microscopy has been developing to bring absolutely unique capabilities in terms of spatial resolution, in terms of energy resolution, in terms of type of physics that can be probed from the electron beams. And if somebody told me 15 years ago that it's possible to have 60 kilo-electron volt electron beam and measure the quasi-particles with the energy of 5 milli-electron volts, I would say that it is a sci-fi. Now you can go to the lab and actually have it done. But there is a downside, or as it may be, it's an opportunity that all these methods generate very large volumes of data. So images are okay. Single spectrum is okay. If you have a lot of data, it's really not enough. We need to have some way to understand the physics behind the data. But this is where we are now. So for thousands of years, we looked at the universe and we saw the stars. Now we can look at the materials and see how the atoms move. So you see a beautiful example of the graphene and silicon atom dynamics when you see how each atom motion. And we can start asking the same questions as people did in astronomy. So what makes the atoms move? So can we, if we can learn the Newton laws from observation of planetary motion, can we learn the forces acting between the atoms from the observation of the atomic motion in the microscope? And then we can ask more provocative questions, because one thing about astronomy is that it's a purely observational science. So no matter how much I tell my wife that I will bring her a star from the sky, we all understand that this is exaggeration. In electron microscopy, this is not the case. We can not only observe, but we can also manipulate matter on the nanoscale or atomic scale. In other words, what you see here is that electron beam kicks carbon atoms one by one, and the remainder kind of reorganizes. So the question becomes, can we control this process and actually use the electron beam to build matter atom by atom? So this is kind of something that we are very interested in, and our team have explored for quite a while. But then you can ask the most important question. So what do you think is the most important thing in life? So what do you always not have enough? There are energy drinks for that. Time, exactly. So the most important thing is time. And each of you who worked with the microscope knows this feeling that you come in the morning, you spend a tremendous amount of time tuning the instrument, then you spend some time acquiring the data, then you have to go back and analyze it, and you have this kind of feeling that what you are doing is highly inefficient. Electron microscope is a very fast tool. So if, for example, the lab X-ray scattering takes half an hour now, it took half an hour when I was a undergraduate student 30 years ago. Electron microscope can give you useful information in seconds. So electron diffraction can be taken in seconds. EELs, according to Gerd, can be done in nanoseconds, but Gerd is kind of always optimistic about this type of stuff. But the problem is that humans are not fast enough. We have tools that can work 100 times faster than we can control them. And therefore, the purpose of the school is to actually try to think about how we can make microscopes faster and smarter and use this intrinsic spectrum of opportunities in terms of efficiency of their use. So what would it take? So some of these things are obvious. So obviously, if we want machine learning agent to run the microscope, we need a way for machine learning agent to connect to the instrument. So this is what is called APIs. This is what is called orchestrators. The reason why you are all here and the reason why the school is held at the University of Tennessee is because our team has built this APIs and orchestrators, sometimes ourselves, sometimes working with the manufacturer. But this is what something that Gerd takes the kind of most blame for. So the second thing is we obviously need some form of machine learning in a very dilute sense. But very importantly, machine learning and APIs is not enough because we also need to know what to do. And that's a very special type of machine learning. So where are we with the school? So what do we want to accomplish overall in the field of microscopy, and what the school should help us to accomplish? So our North Star goal is to accelerate the tool operation to the physical limit of the current instrument. If the electron microscope can run 100 times faster than the human can run it, let's figure out what it takes to make it happen. Obviously, if our microscope becomes 100 times faster, we also need to learn how to make samples because that's kind of match this increase of productivity. And obviously, we also want to get the data that is kind of useful. So in some form, whatever we learn has to fit into the established scientific knowledge. So data should be kind of useful. The great thing for us is that our colleagues in the machine learning community for the last several years have been going all the way out of building machine learning agents that can supposedly do science. But for the time being, they were only 2 weeks ago, there were several papers out of Google and the Future House and Nature. So the ML community builds the automated scientists. So what we have to do is to build the connection between this scientist and the instrument so they can operate on the tools. And we also have to provide the framework that allows them to work together. So to give the automated scientists the physical tools that can be implemented on the instrument. So this is something that we are going to talk throughout the school. So it will include how to cloudify tool, how to build the agentic workflows, how to federate the tools. So this is something that they are going to learn. Now, so what can you expect? So the first important thing is that if we talk about machine learning and microscopy, we need to separate several levels of machine learning use. So the first level, what we did almost exclusively several years ago, was we go to the instrument, we run in the normal way, we take the data, go take the data to our office and analyze it. That's post-acquisition ML use. This is great, but this is not enough because we cannot magically go back and do the experiment differently. So the second level is the real-time analytics. Microscopes can stream very large volumes of data. Human perception is limited to small scan sizes and relatively simple data, so we understand the images, but not hyperspectral data sets. So machine learning can help us to analyze the data in real time, and then still human make decisions based on the analyzed data rather than raw data. The third level is the adding machine learning agent, when we have the machine learning algorithm, whether it's optimization or agent or LLM, that directly control the instrument. So this school would basically focus on this third level. There are other levels, the upstream and downstream planning. So what I mean by that is, imagine that you run the instrument, but ultimately your machine learning agent decides that what you see in the sample is not sufficiently interested and informs the synthesis robot to make another sample. So that's also possible, but that's integration of microscopy with other fields. So, as I said, in order to make all of this work, we still need to build a bridge between the machine learning and the instrument. So this type of bridges are called APIs, Applied Programming Interfaces. So basically, this is something that allows your Python code to tell the instrument what to do, what data to get, what commands to execute, and so on. The status of this type of APIs in the microscopy community is very uneven because electron microscope typically have the cameras and detectors from multiple manufacturers, so they don't have a common API. So one of the things that Gerd and my team has built was the orchestrators that basically work as the single gateway between machine learning agent and the instrument stack control. And kind of that's one part of it. The second part, which is very important, is how do we plan decisions? So that's actually a very interesting thing and something that you normally don't study as a part of the machine learning courses, or at least until very recently. So here the logic is that everything that's done on the microscope can be represented as a sequence of operations. So this is called the workflow. When you sit in front of the instrument, you look at the screen, you choose where to zoom in, you choose where to take the spectrum. That's kind of what the workflow is. So it turns out that if we want to have machine learning agent running the instrument, it has to understand the human intent and be able to convert this human intent in the sequence of commands. This is a very unusual type of machine learning. So all of you heard that machine learning is all about big data. Let's get more data in all our, and that will somehow magically train the giant general intelligence model. That's not how the world works. If we talk about running the experiment, our goal is to get the answers with the smallest amount of data possible because data costs time and money. It's a very different logic. Optimal planning is a very different logic from let's collect all the data and analyze it. So, and that's something that we are going to, again, talk about during the school, how to make the right decisions. And then a very important part of this whole process is making connections on all levels. I mean, first of all, connection matter between the humans, right? The reason you're here, the reason why there are so many people online is because we make a connection to learn and study together. The science, however, also has its internal economics. So, for example, 25 years ago, high-end electron microscopes spent 10 months out of a year being optimized and built, and maybe 2 months a year they have been used. So that was the time when I joined Oak Ridge in 2002. So with progress, microscopes become much more reliable and faster. So in one day, the microscope could study several samples. And there was an economic sense to build the user facilities when multiple instruments are collected in one place and people come to use it as a user, simply because you need a highly specialized experts to run the instrument, but they have a very high throughput, so it makes sense to work with a lot of people outside the world around it. So another example of the science integration is cloud computing. So something that you all know about it. But as I mentioned, for a long time, the basic paradigm of how we use the instruments was always the same. It's human sitting in front of the microscope. Human tells the microscope what to do, looks at the screen, collects the data, makes decision. Then you go to your office and analyze the data. And after that, you publish papers or preprints. So this diffusion of knowledge becomes very, very slow. And the argument now becomes is that we are no longer limited by that. So this is a picture that I made about 10 years ago in Oak Ridge, saying that we can build expert systems to run the instruments. So interestingly enough, during the school, we will show you how the system can be built. And I'm happy to see Levi here, who is a high school student. So one of the things he did in the last half a year working with GERD is build the LLM that runs directly the instrument. So it's kind of pretty impressive. Another thing that becomes possible now is the integration of multiple tools in the geographically distributed networks. So the reason why it is useful is to have access to the data, have access to the code, but more importantly, share the insights and knowledge about how the instruments work. So we'll talk about how to do it and why it's useful throughout the week as well. And just to illustrate that all of this is doable and not exactly a hand-waving argument, you can see the example of Austin sitting in front of the microscope, taking the image, sending in one of the videos, the data is being sent to the world model, Atom GPT, to analyze it. Another example is setting the data to a company in California that will analyze it in real time. So all these things exist and they operational. The interesting part is that we still need to figure out what is their true value proposition, but it's kind of important to be able to do it first. Now, so what about this workshop? So the idea here is that we want to learn how to transition from image quantification to machine learning enabled workflow. So how to make machine learning decisions as a part of your work as the microscopy. So the organizers of this workshop is myself. So I worked in this field for about 20 years. So I started to work on machine learning for experimental physical sciences in the middle of the secondary winter, and started to build and think about microscopes that think for a long time. This being said, I have to take a second step for GERD, because GERD actually got his PhD in 90s. And one of the things that he did while he was a master student was to write a paper on using the neural networks for the EELS analysis. So that was 1995. So if you want to see the living legend who really started the field of machine learning electron microscopy, then GERD is right here. So both of us, in other words, both of us kind of focused on this field for quite a while. So the way the school would be organized, so this is the plan for today. So we typically start with the lectures and demos. Notice one very important thing, which made organizing the school difficult and would be something that would be non-trivial for all of you as well. So generally, there are a lot of classical courses on electron microscopy, which is pretty much hardcore condensed matter physics, beam controls, electron optics, and so on. There are a lot of schools on machine learning and schools tutorials, whatever, EDX courses on the machine learning. Fortunately or unfortunately, if we want to use machine learning in electron microscopy or any domain area, we need to understand both physics and machine learning part. You will not be successful if you understand physics and you kind of don't get the ML part, because in some sense, physics would be limited. You will not be successful if you know a lot about machine learning, but not about physics, because without physics, machine learning is useless. Balancing the two is going to be difficult. If you're going to feel yourself stupid throughout this week, that's absolutely normal. Welcome to our world. That's how we feel ourselves for the last 20 years. But the good thing is that with the LLMs and the code assistants, we can get through the stupid part, at least with programming, much faster. And with the teachers like Gerd, Austin, and everybody who will get tutorial, you can get faster through the part of not understanding the physics as well. So, as I said, so we have lectures, we have the demos of the remote operation. So by the end of each day, we put the hackathon. So hackathon is a very interesting activity that we found to be exceptionally effective in learning new concepts. So basically the way it works is that you have a laptop, you have access to the Google Colab, meaning something that you can use, and then you solve a problem. So interestingly enough, hackathons were developed by the machine learning people as the way to train people, maintain code, ecosystems, what's not. We run regular hackathons as the part of the operation of the centers in the UT, sort of as a way to kind of unlock collective creativity. GERD is the part of the hackathon that maintains the microscopy code system. We run the once a year competitive hackathon where people work nonstop for 3 days to build some projects on ML for microscopy, and then kind of there is some ranking and this type kind of some awards allocation. So last year we got about 250 people participating with more than 25 grants of prize money from industry. But ultimately, hackathon, here we only will start, so it would be a short activity. But the most important thing is that the only way to learn machine learning is to do it hands-on. No amount of the books you read will help you to understand it or use it. You need to try it on. And that's what the hackathon is going to accomplish. So just to summarize, so there are also some basic tenets of what we are doing in this course and how we think about machine learning and physical sciences. So the first tenet is that physics is the best machine learning. We use machine learning to fill in the gaps that physics cannot fill. If we had ideal physical model and physical theory, we would not use machine learning at all. So I know that this sounds weird for the School of Machine Learning and Microscopy coming from the guy who did it for 20 years, but if I am to share with you something that I feel is important, this is one of those things. So a second thing is that where machine learning is important is making decisions. So we think about machine learning for data, and if you don't run the experiment, that's the only thing you can do. The difference between you and people in Google is that they don't have electron microscope. They have to analyze the data that somebody else have acquired. You can build machine learning agents that will run on the instrument and actually get data, and that's what people in Google cannot do. At least even though they're kind of starting to think about it. Then another thing is that only hands-on knowledge counts. So unless you tried something and developed the intuition for physical concepts and how to do stuff, you cannot move forward. So in all this balance between the humans and LLMs that people now talk about, I mean, LLMs can help us learn better. They're not going to get our job done for us, partially because they're not the ones who decide what the job is. And the fourth principle is that time matters. So time matters, your time matter, our time matter, most importantly, microscope time matter. And that's exactly what the value proposition of machine learning is. So this is where we are. Welcome, and if you have any questions about organization, now is a good time. If not, then I will pass the floor to Professor Duscher.